Thank you very much for coming. It's a privilege to be here talking to all of you. My talk is entitled How In-Memory Computing Enables a New Generation of Microservices. And it's frankly a talk I've wanted to give for a while for two reasons. First of all, I work for an in-memory computing company, Hazelcast, which likes to style itself as the leading in-memory computing platform. And secondly, in my own practice as a consultant, microservices are one of the things that I have seen people try very hard to do and not necessarily succeed at doing, right? I was talking to a colleague of mine when I was putting the slide deck together, and I say, I cannot tell you how many conference rooms I've been in with a whiteboard and people sitting in front of their laptops, and I say microservices, someone says stateless, and that's pretty much where the conversation ends. Or, it's like, we're doing microservices. So what this talk is really about is a way to introduce you guys to in-memory computing technology, in-memory data grids, and in-memory stream processing through the lens of microservices. And through the lens of what microservices were originally supposed to be. If you go back to the early 2000s when Martin Fowler and others were writing about kind of the microservices concept and coming out of ways to pervasively do service-oriented architectures. And then, furthermore, to kind of look at how the microservices landscape has changed in the world of AI, ML, and big data, where we're talking about service endpoints that are invoked through REST or gRPC or whatever, but are dealing with much larger data volumes, and the request-response interaction, the request is expected to solve a much harder problem than it was in the past. So very briefly, I will talk a little bit about my background. I'm a senior solutions architect at Hazelcast. I previously held similar positions at GridGain and Gigaspaces, which actually means that I've worked at probably 3 of the 5 significant in-memory computing platform companies, which is really to say there's very few in-memory computing platform companies. I have a lot of in-memory computing domain expertise. I've helped clients build a lot of systems. So one of the things that I did want to do is I don't want to make this a Hazelcast marketing talk. I do enough of those. So everything I say applies equally well to other in-memory data grids and in-memory streaming platforms. So from the in-memory data grid side, that could be GridGain or Gigaspaces or Pivotal Gemfire, to a lesser extent Oracle Coherence. But so think about this as more of kind of a tour of how in-memory computing can enable microservices becoming what we all hoped that they would be. So the structure of this presentation is, in order to kind of talk about, microservices becoming all that we, hope that they could be, is what was the original motivation for them, right? And secondly, how has the motivation for microservices shaped the rules that we apply to them? And what do best practices for microservices mean? And next, when we get into big data and pervasive AI and machine learning, do these rules change? The answer is yeah, they really do. And now that the rules have changed, what kinds of technologies can be used to create best-of-breed microservices architectures? And I would say that the in-memory technologies, either from Hazelcast or from one of our competitors, really do represent, for externalized state and externalized compute in complex microservices environment, the best solution in the stable of common enterprise technologies. So let's go ahead and talk about this motivation for microservices really quickly, right? I mean, the original 3 words used were generally modularity, scalability, and what at the time was called agility. But man, we call a lot of things agile in computer science, right? So I prefer the term evolvability, right? The basic idea being that once you've factored something into independent service modules, they should be able to evolve independently of each other, right? Then you can have small dev teams just cranking out really rapid releases, using CI/CD deployment pipelines, and maybe their sprints are as short as a week, and at the end of a week they release new code, right? And that's that kind of evolvability that we all would like our teams to have, right? Where they can do that, they can explore ideas, they can evolve their product or their service independently of others. So obviously, you know, when we start talking about why these were valuable, we can go back to monolithic legacy architectures for web-based applications. And I put legacy in quotation marks because, quite honestly, a whole lot of web-based applications are still built this way, right? I mean, you have some kind of presentation tier, right? And it could be JSP plus servlets inside of Tomcat if you're a Java developer. It could be Python plus Django. It could be PHP, right? Anything that can serve a dynamic web page or dynamic web content works here, right? And initially, people start. A lot of this started in the late '90s and early 2000s for some of the largest organizations that I've worked with, like AT&T and Apple, where you saw basically what was a simple web application evolve so that in the presentation tier, right, you had business logic being coupled in there, right? And this is your traditional kind of three-tier architecture where, you know, even from the old, you know, mainframe days where this web browser would be a terminal, this would be middleware, and this would be like DB2 on a mainframe. The architecture really didn't change a lot, you know, and in this presentation tier, in addition to serving content, we started building a lot of business logic, you know, very complex servlets. For Django apps, I've seen some really complicated Django apps in my time. The downside to this is that, you know, if you want to take your WAR artifact and deploy it, well, you probably have to have like 5 teams all deploy their web app at the same time and go into this massive single presentation tier, right? Because everything is tightly coupled. And it makes assumptions about other components. And if any of those assumptions are broken, that's too bad. So obviously motivation one for microservices in the traditional sense was modularity. You wanted to break down that monolithic service plus presentation tier into a very simple presentation tier that might serve some static content, and then a variety of independent service endpoints. I'm using the Spring Boot logo here just because it's the most common way of packaging request response microservices in the Java world. But this could be any dynamic web request response technology. And you know, the individual microservices may make service calls to each other, and the presentation tier may make calls to them. In some cases, for AJAX applications, it's even the browser making calls, right? So already we're seeing modularity, the cognitive weight has gone down. Like, provided we think of these as independent things communicating through well-defined APIs, that's a lot better than whatever the heck this is. The next motivation, of course, was scalability. And that was basically the idea of, you know, well, you want more capacity for your customer loyalty service, but you don't really care about your inventory management service. Just deploy more service instances, right? And a lot of the control plane technologies that we have now that we're talking a lot about, like Kubernetes and OpenShift, et cetera, really had this idea at their core, right, of being able to support a control plane for dynamic scale up and scale down, which should indicate sort of how important this notion of scalability is. And we'll talk about some of the impacts of scalability as a design requirement for microservices a little later. And that's really where in-memory computing comes in. Finally, evolvability, right? Dev team A and dev team B should be able to deploy services at their own rate. If one team has 1-week sprints, another team has 2-week sprints, we don't really care. Furthermore, we should support the ability to potentially have multiple service versions coexisting at the same time, which is fine, provided they all follow the same API contract. So these are really, you know, the reasons why people started doing microservices. And the question is, you know, what are the, you know, if these are the goals that we want, then how do we have to build our applications? What are the rules for building applications like that? And how do those rules change when we get to very large scales, right? So the rules, at least from the initial motivation, was be lightweight. Do one crisply defined, cohesive thing and do it well. And that came from modularity, right? I mean, this clearly processes customer loyalty requests. This clearly processes inventory management requests. No one knows what this does, 40 different functions all amalgamated together. Next was be stateless. Don't keep any sticky information in a service instance. The point being that any request should be able to be fulfilled by any instance of a service. So, this caller doesn't really care whether they hit instance 1, 2, or 3. There's nothing special or sticky. There's no session. There's nothing permanent that in any way hampers even load balancing and horizontal scaling. Finally, services should be implementation agnostic. Developers should be free to choose their own implementation languages, tools, etc., and to change those at will, so long as the public API contract of the service remains the same. And this is really the evolvability criteria, right? So when we get into a new generation of microservices, though, like recommendation engine services for films and fraud detection services, how do these rules change? I mean, clearly, we got to do something about stateless because, there is state. Frankly, there's a lot of state. There's user profiles, there's films, there's a lot of information here, right? There's a whole past history of credit card transactions for a card member that you'd like to run some kind of ML classifier against. So the unifying themes of these new generations of services are large data volumes, pervasive use of AI and ML, and most importantly, because I had already sort of talked about the Kubernetes OpenShift revolution, service instance counts that scale up and down dynamically using these various cloud-native operations and scaling frameworks. And to add to it all, in some cases, there's a desire, particularly in financial services and capital markets, for response time as low as a few tens of milliseconds between when the request is sent to the service and when the response is given. Because as I'm sure you guys all know, in many cases now, when you actually compose something that's going into a user experience, you might hit 12 or 15 different service endpoints, and then have to compose the results of those, right? So you can't really have any one of them be sort of like on the tail of the latency curve in a way that slows everything down. So, do the rules still apply? Well, they kind of change a bit. Stateless becomes state externalized. I'll talk about what that means in a second. And lightweight becomes compute externalized. To understand what I mean by state externalized, we got to think for a second about where the stateless mantra came from. If you allow service instances to store state, then you're in a nasty little predicament. You might have a load balancer. However, if you're looking to make a call to do a fraud check on customer ID 17, customer ID 17 is located in instance 1. You're always hitting instance 1. Instance 2, not involved. You can't go to instance 2, right? So this is what we would call stickiness. I mean, you guys probably know this from caching session information and things like that, right? This is where the idea of statelessness came from. But, what if you have real states, real state information to deal with? Because customers are a thing. The films they watch are a thing. All of the credit card charges that they've ever made are a thing. It is state. We would say that state needs to be externalized. It needs to be taken out of the service instance itself and put into some kind of service data store or data plane. And at this point, this call can come in and it can hit either service instance. Doesn't matter, because the service instance itself is going to go to the backing data store, get the data that it needs to prepare the response, and then send it back. So one question becomes, great, let's externalize our state. We got real state to deal with, can't get around it. Where do we put it? I mean, a lot of people think, oh, man, I love MySQL. I know it really well. I like Postgres. It's free. Relational databases are a really poor choice for this for several reasons. First of all, they're slow, and I'll get into expanding on that with some real numbers in a second. Next thing is that, NoSQL databases are designed for horizontal scale-out. Most traditional relational databases are not. They follow a scale-up model, right? So if you need more capacity, you have to get a bigger server. So that scale-up design of a traditional RDBMS systems really conflicts with this dynamic scale-out of microservices. I mean, we expect to go from 2 instances to 50 by flipping a switch, and there could be an Ansible playbook or, you know, something coordinated by OpenShift or whatever. It's going to deploy, and those services are going to start, right? So the other thing is that the object relational impedance mismatch, which we've all dealt with, we've all written Hibernate code, we all know what this is about, means that you have to go through ORM even for short-lived objects that microservices have, you know, deal with, right? There was a great article in one of the more prestigious industry rags like eWeek or InfoWorld. This is back in 2013 or so, and it was a study done by Gartner or Forrester that said that something like 30% of all CPU cycles in data center applications are spent doing object relational mapping. Furthermore, I mean, a traditional RDBMS is a fixed schema model environment, right? I mean, and you know, you want to change your schema, find a DBA, get them to issue an alter table statement, right? It's a shared environment with schema enforcements. That's great, but that really has a problem when we get into this idea of evolvability. We want to go back to this slide where we've got dev team A, dev team, and they're iterating very rapidly, and then there's dev team B, they're iterating very rapidly. You know, how does this work? Is there like a change request ticket that we file with the DBA? I mean, the point is that agility, that evolvability can be slowed down, right? So what alternatives are there? Well, there's really 2 major ones in the library of common stuff you would find in a data center. The first are NoSQL databases like Cassandra or Mongo. They have some definite advantages. They're schemaless. They have a more object-based style of storage. And they scale horizontally, right? So they can scale as the service instances scale. There's also in-memory data grids, or IMDGs, which are admittedly a more exotic technology. And you guys might have heard that there's a lot of buzz about in-memory computing, so I'm going to actually talk about what an in-memory data grid is and why you might want one. We make one at Hazelcast, GridGain makes one, Oracle has one in the form of Coherence, although it hasn't been updated for a while. But they're not terribly uncommon, just not something that you might have worked with yet, but I'm going to tell you why you should. This is a great slide, and if you know this book from Brendan Gregg, Systems Performance, Enterprise, and Cloud, it's actually one of the best books on building scalable systems I've ever read. It was originally published in 2013. There was a 2018 update, and what Brendan did was something kind of cool. He took actual latencies of common operations or storage mechanisms in computing, right, whether that's a CPU cycle or a cache access, reflected them in nanoseconds and microseconds. But those are, you know, we all know, you know, that, you know, it's 1,000 times, but then what does that really mean? And so he scaled the latencies, and you'll see that a main memory access against a DIMM, the scaled latency is 4 minutes, right? The best SSD you can buy, the Intel Optane Data Center SSD, with the 3D X-point bubble cells on it, 7 hours. 4 minutes and 7 hours is significantly different, right? This is microwaving something. This is a transcontinental flight. So, you know, memory, it's faster. Don't think I needed to tell you that, but I hope this makes it really clear. An in-memory data grid, I pulled this slide directly from our marketing deck, which is great. Didn't have to make it myself. It's a data model distributed across many servers at a single data center or across multiple data centers and or clouds. So there's a lot of marketing speak here. Yes, we support multiple data centers and clouds. But basically, it's sort of like a NoSQL database or an object store where all data is stored in the RAM of the servers, right? Servers can be added or removed to increase RAM. Now, one thing that you that I should tell you is that yes, if your server loses power, data is lost, which is why all of the in-memory data grids for high ability features contain various replication rules. The replication rule could be synchronous or asynchronous, but the idea is that for every primary piece of data or every primary data partition, there's a backup data partition located elsewhere in the cluster. So you can survive power failures. Hazelcast and most of our competitors also offer WAN replication across data centers, and we do this in clever ways by compressing and using Merkle trees to try to determine if there's any entropy between the data in one data center and another. But I mean, the point being is that, you know, if you want to do replication across data centers, you can. I mean, there's latency involved, but it is possible. So well, I know when I say in memory, a lot of people are like, oh my God, I could lose my data. Well, let me say, like, very few people lose their data with modern IMDGs, unless you do something kind of stupid. The data model is non-relational and is object-based. And we have language bindings for Java, C++, C#.NET, Node.js, Python, Go, and Scala. It's resilient and non-disruptive even in the event of failure. So I would just say, for instance, with Hazelcast, it's frankly, if you have a 5-node cluster, you power down one of the nodes to do a rolling upgrade or routine maintenance on it. It's not even an issue for client traffic. I've never seen it really impact much of anything. So much so that it's the standard way of doing maintenance on in-memory data grids. The backup partition located elsewhere in the cluster is promoted to become the primary partition for that data, and then another backup partition is created elsewhere to retain your replication SLA. So kind of talking about the features of IMDGs and Hazelcast in particular, and how this fits into microservices is kind of where we're going to go now, right? So Hazelcast is very implementation agnostic. We've got clients not just for Java, but for C#, Scala, Python, Go, Node.js, and most other languages and runtimes. The most other languages and runtimes here, if you're a Ruby developer, for instance, here's the thing. So we at Hazelcast have 2 tiers of products. We have enterprise products that are commercially licensed that you have to pay for, and we have our base in-memory data grid is open source. It's available under the Apache license, and we actually have a lot of people outside of Hazelcast that contribute to it. And one of the things that has come from the community are language bindings for Ruby, even Haskell if you're really into functional programming, but those are community maintained. So the ones that you see listed here are officially supported. So this lets development teams choose whatever languages, tools, and libraries work best for them. You know, a data science team might prefer to work in Python instead of Java, right? And this is, you know, kind of crucial for success in microservices environments for the reason that I talked about earlier. I mean, we don't want to read this big blob of text. Let's just go back here, right? Where, you know, dev teams are free to choose their own languages and tooling. They're free to deploy when they want to. They can deploy at very rapid cadences. You know, sprint cycles of a week are not uncommon. And you know, that's why I would say that, you know, our implementation agnostic features are one of the selling points for Hazelcast, for example, compared to some of our competitors. So the other nice thing about IMDGs is it has to be a clustered solution. You cannot have an in-memory data grid that is not a clustered solution because you have to have a backup replica, right? So scalability is built into these products at an extremely fundamental level. And if you really want to talk about like the consensus algorithm that we use and what parts of the system run in CP mode versus AP mode, I'm happy to talk to you about that individually afterwards. I'm not going to go into that level of detail here, but clustering is a core part of these products. And, you know, here we've got 2 payment processing service instances and a 3-node in-memory data grid cluster. Oh man, we add 2 more instances, we need more data. Hey, that's no problem. Now we've got a 4-node cluster, right? And that's because elasticity, replication, and fault tolerance have been built into these products from the beginning. As I said, they have to be, given the volatile nature of RAM. So So with all of this said, I actually believe that IMDGs represent a near ideal state storage mechanism for microservices, right? Data is kept entirely in memory. Data is stored in its native object format. There's no object relational mapping that occurs. I do have to tell you one kind of secret, though, which is in order to get this language interoperability, which means that you can put a Java POJO into the data grid and get back a C# object, we actually do have to convert that from its Java form into a very lightweight binary serialization format that is platform neutral, right? So you could think of it as something like a protobuf or Apache Avro, but optimized for storage in the in-memory data grid. So while there's a little bit of marshalling, there's no ORM or even significant format conversion. It's not like you have to convert it to JSON or something like that, which you'd need to do in Mongo, right? Load balancing, once again, is built in at a very fundamental level to these products. Happy to talk to anyone in detail about exactly how that works. They have a very flexible schema model, which is to say, just deploy an object of a different class to go from, payment record V1 to payment record V2. One of the things that some of our competitors have that we do not yet have in Hazelcast but are adding is the ability to undeploy class schemas. So when you're done with, payment record V1, you can actually undeploy that code, right? And we're not talking about like copying jars or anything like that. This is all done through a distributed class loader for those of you who are Java nerds, yeah. I mean, at a very basic level, the core API is key value, but we also have a very rich query API based on predicates. So basically, what's in a SQL where clause? It's like if something is less than, greater than, and all of the normal Boolean operators that you would expect apply there. You can actually write very complex queries. I mean, the expressive power is equal to that of SQL, but I'm actually going to tell you why you shouldn't do that a little later in this presentation. And we have multi-language and platform support. Here's the thing about IMDG deployment options, and this is I'm going to talk a little bit about why I said that sometimes if you pick one of these, you need to be careful about your queries. Hazelcast is a Java-based solution. It can be deployed into an existing application, or it can be deployed in client-server mode. If you deploy it in client-server mode, you get basically your Hazelcast cluster of 4 nodes. These are servers dedicated to Hazelcast. They do nothing else. And there are Hazelcast clients that live in each of these instances that talk to them, just like a JDBC or ODBC database access client. You can also, if you happen to be a Java shop and are running a JVM application anyway, particularly Spring Boot, Tomcat, WebLogic, JBoss, all very common, you can actually put the IMDG server instance inside of your existing JVM-based application. And one thing that I will say is, well, in-memory data grid is probably storing a lot of data in memory, right? What about like garbage collection in Java? So for our commercial product tier, we use native code, right? It's native code. Everything is stored off the Java heap. It does not impact whatever else is happening in that particular Java process. Either case, Hazelcast IMDG provides a great state externalization mechanism, right? Here's your unified data plane. Each individual instance holds a Hazelcast client. They all talk to the IMDG cluster. The IMDG cluster scales up and scales down as needed. The unified data plane has several features and implications. One is that different types of microservices, in this example we have payment processing microservices and device management microservices, share a single Hazelcast cluster to store their externalized state. The cluster elastically scales up and scales down with the microservice counts. And because data from different services is kept in a unified plane, it can be queried and joined in a unified way. So That's kind of cool, actually. If you need to do complex reporting, you can actually broadcast code into the cluster and do some sort of like a scatter-gather type operation where, you can put together reports using co-located execution in the query engine about what is actually going on, and what the service data is saying, because you might want to say, determine what kind of devices, people are buying, right? I mean, that might have to be, in this example, assuming that these microservice instances live in their own isolated multi-tenant portions of the cluster, but someone from the analytics or data science team has permissions to join across that, you could accomplish that. They'd be isolated as far as these developers are concerned, but from an analytics standpoint, it would be a single unified data plane. And Hazelcast enterprise security permissions in this case would enforce multi-tenancy boundaries. What I will say, though, is this. If you do that, be very careful what kind of queries you run here. I have had customers be like, and I'll step back and say, we have not introduced an ANSI 99 SQL compliant query connection to our data grid at Hazelcast yet. Two of our competitors have them. We are introducing one, and I somewhat am concerned about this, right? Because distributed SQL is hard to do, and I previously worked at GridGain, which does have distributed SQL, and it was very difficult because customers would say, well, I want to take my transactional grid that has, 21 servers and 6,000 clients, and I want to run ad hoc queries on it. Don't do that, right? I mean, so the unified data plane is both very sexy in the sense that it's great for business decision making, but you can seriously slow down your transactional throughput, right? If you have queries that happen to not be performant. There's also the embedded data plane option, where basically if this is a JVM application, you just stick the Hazelcast server node inside of it, and this is as simple as adding one jar dependency to your Maven project POM file. The objects will, in the same way, you need at least two nodes to do this, right? So that they can mutually back each other up. But what you basically have is a Hazelcast cluster as a sidecar on your existing microservice instance. This has certain advantages, right? So I would say, yes, no single unified data plane. So operations teams can deploy, manage, and upgrade. Basically, development teams can do their own ops vis-a-vis the data plane. There's no one needs to maintain anything centralized, and that, I would say, kind of helps with this notion that we talked about at the very beginning of evolvability, where teams are iterating very rapidly and they're dropping out new releases on a weekly sprint cadence. Frankly, it doesn't really matter which one you pick. They're both good. They both have their pros and cons. It's just my job to make you aware of it. The last thing I'll say before we move on to our other topic, and then I'll take some questions, is in Hazelcast IMDG, there is a lot more than just state storage that is useful in a microservices universe, right? So we also have in our CP subsystem, which, as you might guess, runs in fully consistent mode and requires consensus. Most everything else runs in AP mode, if you're familiar with the CAP theorem. If you need things like locks or countdown latches or semaphores, and sometimes these are important in microservices environments if you have like and I've seen this quite a bit with brick and mortar companies that have like a legacy mainframe, they can only make X number of calls at a given time, and they need some kind of countdown latch or semaphore or something like that that will basically provide concurrency control. These are all there. Basically, these are what we would call server-side cluster objects, and you get a client-side proxy to them, and you do what you want. So the last thing I'll talk about is complex compute. So this has become something that has become more and more significant in the microservices world, and I'll actually give a brief use case later. you know, if you want to do anything involving AI or machine learning, or you have some kind of microservice endpoint where you hit the endpoint with, say, an HTTP transaction, a post, and that post payload is like a 300 megabyte blob of CSV delimited text, and suddenly you have to take that and do a bunch of ETL operations on it in order to get it somewhere where you need it in your organization. You know, that's a compute-intensive ETL transformation operation. We at Hazelcast thought a lot about this, and we particularly thought about the ETL case and data in motion. And so we developed Hazelcast Jet, which is the second aspect of the Hazelcast platform. Hazelcast Jet is a third-generation stream processing engine. Before I, try to talk about the wonders of Jet, one of the things you might think is, oh man, stream processing. Like I don't have any like IoT devices. I'm not like getting stuff from factory robots. But all stream processing is actually just a different way of reflecting computation than our traditional imperative model, right? And GPUs are programmed this way. So if you're familiar with like CUDA and the GPU APIs, they generally use a stream processing model. When people are mining Bitcoin on their AMD rigs, then this is how they're doing it, right? So the thing about stream processing is that if you do have massively parallel systems like GPUs or very high core count CPUs, the stream model, as opposed to the traditional imperative model, tries to avoid synchronization as much as possible. You know, you see each evolution of data as in its own stream. And you try to synchronize as little as possible. So there are much fewer locks and mutexes and things like that. Stream processing has been around a while. Like Apache Hadoop introduced computation that was a series of map and reduce phases, which is basically a stream. To this day, if you do stream processing programming, you'll notice that map, flat map, these are the common, core tools of stream processing. They come from functional programming and from ideas in Hadoop. Around 2015 or so, Spark appeared and began to replace a lot of Hadoop installations for kind of complex analytics, characterization, classification. We all know what Spark is used for here. So Spark, of course, says, well, we're a stream processing engine. And I will also say that Spark directly competes with Hazelcast Jet. So one thing you might wonder is, like, why not use Spark? Because, at the end of the day, you've definitely heard of Spark. You probably haven't heard of Hazelcast Jet. Jet is significantly faster. There's another thing that's kind of really awesome about Jet too, which is Jet is built atop the in-memory data grid. So every Hazelcast Jet instance has an IMDG instance inside of it. So you can do stateful processing, aggregation, windows of time. You can build up events that are streaming in. And you can also, because the in-memory data grid is sort of like a database, you can preload data into the data grid, and as stream data comes through, you can enrich the data in flight, or you can change its form, right? Would be like, for example, when the data comes in, it has a key that's some kind of UUID. You do a lookup in the in-memory data grid, and you get the whole object that goes along with that, and then you enrich the data while it's in flight, right? But Hazelcast Jet clusters elastically scale just like IMDG clusters. Here are some benchmarks that I've included. Our most direct competitor is probably Flink. Flink chokes a little bit on very large data sets. Admittedly, Spark with Tungsten performs pretty darn well. I would still say Jet in blue is performing the best. I mean, obviously any vendor is going to say we've got the best benchmarks, but if you read the blog post behind this benchmark, which I believe we have linked to in here, we did everything we could to give Spark the best opportunity. Why Jet? I'll just say that Jet is actually a great compute appliance for microservices, right? I mean, it's based on the standard Java 8 Streams API. So finding people who can program stream processing systems is kind of challenging sometimes. Spark is heavily Scala-based, right? If you can write Java 8 Streams code and you know about like .map and .flatmap and all of that in the Java 8 Streams API, .collect, you can already write Jet code. It's clustered and dynamically scalable. If you need more compute power, just scale up the cluster. This can actually be done while jobs are running. This is true for Spark and for all of these products as well. If you can express your computations as stream operations instead of traditional imperative operations, you'll be able to do a lot better in terms of parallel scalability, right? And so if you come by our booth, we have a partnership with Intel going right now regarding running Jet on very high core count Cascade Lake CPUs. In the same way, you need more compute power. Here's your film recommendation engine. You add more instances, boom, your Jet cluster goes from 3 nodes to 4 nodes. Nothing is interrupted, right? I will share an example use case and then take some questions. So this sort of puts together IMDG and Jet into one coordinated picture. So the customer is a large global creative and media company. You have heard of them. The application is a recommendation engine that helps people choose where and when to buy ads on TV. It's delivered as a SaaS solution, right? So basically the goal of this is, if you want to target men between the ages of 30 and 45 with annual incomes in excess of $75,000 who routinely drink 3 or more diet sodas per week, we can tell you where to buy that ad space. Basically that's the request. The response you get back is, well, buy it on CNN in Chicago, Detroit, and Milwaukee between 8 and 10 p.m. in the evening. That's the best place to spend your ad dollars. So there is a lot of data involved, like terabytes of data, and there's quite a bit of ML type secret sauce here that, frankly, I wasn't exposed to because our customer kept it very secret. But the overall application architecture looked like this, right? You would have a simple web server, it was Tomcat, that basically handled the job submission UI, right? And then once those, and the job, by the way, was, okay, I'm going to fill out a form and I'm going to tell you the demographic I want to target, and I want you to run a process, right, and tell me where I need to buy ads, right? As a practical matter, this process actually took about 10 minutes. So Jet, when it's running here, is not running in interactive streaming mode. It's running in batch mode, which is basically, as you might imagine, just take a large input file, generate a giant output file. There were various microservices that were put together, such as the job submission service, which had some throttling and back pressure logic built into it, a job progress service, and then finally this result reporting service, which basically did the formatting and generated reports and kind of culled all of the stuff that was determined, which often was a lot of material for someone to digest. But so as I said, every Hazelcast IMDG, this is the Hazelcast IMDG logo, and this is the Jet logo, every Jet node is also an IMDG node. So what the job submission service would do is it would prime the cluster with a bunch of data that it needed in the in-memory data grid, and then at the Jet layer, what would happen is the process would be kicked off, and that would perform this batch processing using a streaming model, enriching and aggregating as necessary, pulling from and writing back to the IMDG, and then once the report was done, it would be sent back. So this system is going live as we speak. It's a 27-node Hazelcast Jet plus IMDG cluster, and that's an example use case of how I feel like you can build some really amazing microservice endpoints using in-memory technologies. So we've got some technologies and integration slides here that are not for discussion. Therefore, when you guys get a copy of this slide deck, if you want to know how we integrate with Spring Boot and Kubernetes, etc. But I'll take some questions now. Okay. So any questions? Yeah, go ahead.
Just one thought about, so this entire data store is in memory. How do you deal with a state that's years old and just terabytes large? I mean, it's all of that state isn't stored in memory, right?
So there are two possibilities, right? The first is to demand load it, right? That's what happens. That's what happens in this application. The job submission service actually handles the demand loading, right?
Don't you lose a lot of your performance gains if you're reading and writing
Well, the thing is that it just so happens that there is a lot of spatial and temporal locality in what people ask for, right? If they're coming up on the Super Bowl, you're asking for a lot of the same thing. In fact, caching itself works on top of spatial and temporal locality. So it just so happens that you're generally loading a very small amount of data, right? The other possibility, and this is something that we are doing, is tiered storage, where you have an all-in-memory model, but what you also have is the ability to basically keep the entire data set larger than will fit in memory on disk, on an high-performance SSD that's attached, to the server node itself, right? And for some generation of hotness, the hottest fraction of data will be kept in memory, and the colder portions will be paged out to disk. Now, what I do want to say about the latter model, it does have one advantage, which is if you want to query the data using that cool predicate query API that I talked about, everything you query has to be loaded into Hazelcast IMDG. So it's not like if you let's say your backing store is Cassandra, and you demand load from Cassandra. It's not like if you issue a query against Hazelcast, it's going to say, well, I didn't find the data in Hazelcast, let me talk to Cassandra and see if it's there. So demand loading will not allow you to fully query the full data set, right? Whereas tiered storage will, right? But there's a lot of complexities around tiered storage, and thankfully one of the things that we have and will keep, even with tiered storage, is the fact that a backup replica will be kept elsewhere in the cluster. So we can eliminate, we hope to eliminate the disk out of the critical write path, right? You won't have to do an fsync or something when data comes in, because you'll confidently know that somewhere else in the cluster, someone else will succeed in writing it. I hope that answered your question. Yeah. Anything else? Oh yeah, go right ahead, please. Yeah, I'm happy to. So Redis is actually a great tool. Redis is a cache. It's not an in-memory data grid. It doesn't have the rich query functionality, and more importantly, it's actually on this slide. The way that a lot of very complicated stuff, whether it's querying or reporting or whatever, is done is through this executor services, right? So basically, we provide the ability to run co-located arbitrary Java or C# or any of the supported language code on the servers that hold the data, right? So the data is sitting there basically hot and ready in its object format. You've got a bunch of machines that have CPUs. We provide an entry point that basically treats the cluster as a massively parallel compute grid, right? And that's dramatically different than a traditional cache, for instance. Yeah. Yeah, go ahead. Yeah.
How do you weigh those?
Well, I'll say this. Embedded, if you have an existing application and you just want to add in-memory state storage to it, it's way easier to embed it, right? Just add it to your POM, rebuild your artifact, and you're good to go. Okay, we're going to have to stop, unfortunately, but one of the things that I will say, just to finish this question, then we'll stop, is that if you have a bunch of different services and they're all storing data in themselves, your data may be stored in like a polyglot way through like 70 data grids in your organization. We have customers like that, but it's not very easy to do unified analytics on that. So that's what I'd say. Maybe use embedded mode to get started, and then once you're ready and you feel like you have the operational expertise, have a dedicated cluster with dedicated ops. Hope that answered your question. Great. All right, thank you.